For the first problem, we're asked to draw the mechanism for the first four reactions, if applicable, and predict the major products, again, if applicable for each reaction. So for this first reaction, this is interesting. We have our chloride anion as our what could be nucleophile, and our O-ethyl group as our leaving group. So in this case, if we think about the mechanism, first of all, it's probably not going to happen. And the reason why I say that is because thinking about the stability of the leaving group, you can't get much more stable than the chloride anion. So if we were to think about the nucleophilic attack on the carbonyl carbon, where we attack the carbonyl, push these electrons up, that gets us to this intermediate, where now we have an oxygen with a negative charge, we have our O-ethyl group, and we have our chlorine. When these electrons come back down to kick off the leaving group, the better leaving group in this case is our chloride anion. So what that means is what we get back to is our starting material. So we're going to form our starting material, which means overall for this, if you weren't to write this out and show that essentially the starting material is the major product, you would say no reaction. And this is determined by the stability of the conjugate base. So that chloride anion, you can't get much more stable than a chloride anion as your conjugate base. When you have your oxygen with a negative charge on it, your alkoxide anion, that's a fairly strong base. And again, you could look at the pK of the conjugate acid of both of those to make a more direct numerical comparison, but it's pretty clear that hydrochloric acid is a much stronger acid than ethanol would be. For this reaction, here we have a strong nucleophile, strong base, so if this were to act as a nucleophile, we could attack the carbonyl carbon, move these electrons up. However, we have a very acidic proton here. So in this case, if we've got a strong base and an acidic proton, that base is definitely going to deprotonate that proton first. So here our electrons are going to attack that proton, move those electrons to there, which gives us our then conjugate base, which is our acetate anion, so our deprotonated carboxylic acid. And then we also have ethanol, and ethanol is our conjugate acid, so ETOH. For this reaction here we do have a very good leaving group. Here we have a somewhat weak nucleophile, but I think this reaction can still go. So our lone pair on our oxygen is going to attack our carbonyl carbon. We're going to move these electrons up to get us to our intermediate, where now we have a negative charge in the oxygen. We have our Cl, and we have our OET, still with a hydrogen attached to it, and a positive charge. Now, looking at the stability of the conjugate base, ethanol and chlorine are probably similar in stability. However, we have a very acidic proton here. So if we add another equivalent of ethanol, we can deprotonate our acidic proton to get us to a slightly more stable intermediate, where now we still have a negative charge on our oxygen. That methyl is there, our chlorine is still attached, and now we have our O-ethyl. Now our electrons can come back down and kick off the best leaving group. Our chloride anion is much more stable than our ethoxide anion, so that is going to be our leaving group, and that gets us to our final product, which is now our ester functional group. Specifically, this is ethyl ethanoate, more commonly referred to as ethyl acetate, but ethyl ethanoate is the IUPAC name for this, and we formed that from our ethanoyl chloride. I'm not going to ask you to name the acyl chlorides for this, but the IUPAC name for this is ethanoyl chloride. It's commonly referred to, if you just have two carbons in your carbon chain, acetyl chloride. Alright, for the next reaction, again we have a relatively strong base. So that nitrogen, it will take a proton if it can. In this case, if we have an acid catalyst in the reaction, then it's definitely going to take that proton. So in this case, our products are going to be the original ester, again, ethyl ethanoate, plus the protonated version of our amine, which is now NH2, Our nitrogen has a positive charge, and we have an ethyl group and a methyl group attached to it. For the next reaction, if we have our amine or even two equivalents of the amine, we can then go back to attacking the carbonyl carbon of our, in this case, ester functional group. So here we're going to do a nucleophilic attack on that carbon. That pushes those electrons up. Now we have an oxygen with a negative charge, and we still have our oxygen with our ethyl group attached, and now we have our nitrogen with a positive charge and an ethyl and a methyl attached to it. We have another equivalent of this available, so that is going to be the strongest base that we have in solution. So our nitrogen with our ethyl and methyl, and one pair of electrons can deprotonate that to stabilize our intermediate. And now our oxygen with a negative charge, so our alkoxide anion can come back down and form the double bond and kick off the more stable conjugate base. In this case, the oxygen with the negative charge, oxygen's more electronegative, it can handle that negative charge more easily. It's more electronegative than nitrogen, which is why nitrogen does not want that negative charge, so our more stable conjugate base will form, and that gets us to our final product, which is our amide, where we still have a methyl group there, and we have a nitrogen, which is attached to a methyl and an ethyl group. So we were able to form our amide functional group from our ester functional group in this reaction. All right, for the next, provide IUPAC names for the following carboxylic acids. If we have a carboxylic acid functional group, that needs to be part of the parent chain. So this is going to be, it's going to end in ic acid. In this case, looking at our carbon chain, we have 1, 2, 3, 4 carbons. We have 1, 2, 3, 4, 5 carbons. So that's going to be our winner, which is longer than 1, 2, 3, 4 carbons. So the 5 carbon chain is our longest carbon chain, incorporating the carboxylic acid functional group. The carboxylic acid functional group will always be carbon number 1 on the compound. So this is carbon number 1. Here's 2, which has an ethyl group. 3, which has a methyl group, and then this ethyl group here is part of the parent chain. So don't let that dash confuse you. This ethyl group is part of the parent chain. So we have an ethyl group at carbon number 2 and a methyl group at carbon number 3. So as I was saying, so we have a 5 carbon chain. So normally we would say that's pentane. However, if we have a carboxylic acid, we take out the E and add oic acid. So this is pentanoic acid, and we have an ethyl group at carbon number 2 and a methyl at carbon number 3. So this is going to be 2 ethyl, 3 methyl pentanoic acid. Now at carbon number 2 and carbon number 3, we also have stereocenters. So to assess these stereocenters, draw the hydrogen in on a wedge. That's ranked 4th. That carbon is by far ranked 1st. That carbon's 2nd, and that one's 3rd. So again, carbon number 1, carbon number 2, carbon number 3. This has a counterclockwise rotation, however 4 is in front, so this is an R stereocenter. For this carbon right here, looking at what's attached, we have CH2, CH3, and CH. CH wins, CH2's 2nd, CH3's 3rd. We have hydrogen again on a wedge, so that's in front. So this is going to be the opposite of what I assess. So here again we have counterclockwise rotation. Normally that'd be an S stereocenter, but since 4 is in front, it's the opposite. So we have 2 R stereocenters. So this is 2R, 3R, 2 ethyl, 3 methyl pentanoic acid. For the next compound, we have carboxylic acid functional group again at carbon number 1, and here's carbon 2, 3, 4, 5, 6. So we have a 6 carbon chain. This is 6 carbons is normally hexane. I'm going to take off the E and add oic acid. We have 2 methyl groups at carbon number 2, 3, 4, 5, and 1 methyl group at carbon number 5. So this is 2, 2, 5, trimethyl hexanoic acid. On this compound right here, again, we have our carboxylic acid at carbon number 1. This has 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this would be octane, but instead of drawing the E, I'm going to say oic acid, octanoic acid. And at carbon number 1, 2, 3, 4, 5, at carbon number 5, we have a methyl group. This has a stereocenter. And at carbon number 6, we have an ethyl group. So this is going to be 6 ethyl. I'm putting that first because E comes before methyl. 5 methyl octanoic acid. Again, on this one, we have stereocenter, 1 stereocenter. So this stereocenter right here, if we put hydrogen in the back and then rank the carbons attached, we've got CH2, which loses to CH, so this is ranked first, that's second, that one's third. Hydrogen's in the back, which is convenient. This has a counterclockwise rotation, so if I go 1 to 2 to 3, that's a counterclockwise rotation, which means we have an S stereocenter. I don't need to number this because we only have 1 stereocenter. For the next compound, again, we have a carboxylic acid, that's carbon number 1, 2, 3, 4. At carbon number 4, we have a cyclopentane ring. Carbon number 1, 2, 3, 4, 5, 6, and again we have a 6 carbon chain as our parent chain. Also on this carbon we have a stereocenter right here, so let's go ahead and assess this stereocenter. Hydrogen's in the back again, which is convenient. Here we have CH2, which ties with CH2. That CH wins, so that's going to be ranked first. This CH2 goes to another CH2 right there, so that one's going to be second, where that one was a methyl, so that one's third. So in this case we have a counterclockwise rotation, again, and S stereocenter. Now at carbon number 4 we have a cyclopentane ring, so we're going to call this S4 cyclopentyl. So again, our ring is a substituent on here, so instead of cyclopentane, it's cyclopentyl, and then hexanoic acid. So S4 cyclopentyl hexanoic acid. For the next, provide an IUPAC name for the following amides. Again, we're going to replace the E on the parent alkyl group with, instead of oic acid like we did here, now we're going to replace that E with amide. So here for carbon number 1 is right there. So this is a 1, 2, 3, 4, 5, 6 carbon chain. So hex and amide. And on carbon number 1, 2, 3, we have a methyl group, which is a stereocenter, and 4, 5, we also have a methyl. So this is 3,5-dimethyl, 3,5-dimethyl, hex and amide. And on this carbon, like we said, we have a stereocenter. So this is ranked CH2 ties with CH2. Carbon with a double bond oxygen beats carbon with some carbons attached, so this is going to be ranked first. That's second, that's third, and hydrogen's in the back, that's fourth. And this has a clockwise rotation or an R rotation, so this is R 3,5-dimethyl hexanamide. All right, for the next one, this is a little bit more complicated because now we have substituents on our nitrogen. We do have an amide, and for our parent chain, we still base that on the number of carbons connected to this carbonyl carbons, where we have 1, 2, 3, 4 carbons attached to the carbonyl carbon of our amide functional group. We also have a methyl group at the 3 position. So this is N diethyl. So essentially specifying what's attached to the nitrogen, we clarify that attached to the nitrogen we have, in this case, 2 ethyl groups. And now looking at the parent chain, so the carbonyl carbon of our amide functional group, we also have a methyl group at carbon number 3, so 3 methyl. And this is 1, 2, 3, 4 carbons. So butane would be butane. Again, I take off the E and replace that with amide. For this compound, looking at all the substituents we have an isopropyl group on our nitrogen and we have a methyl group on our nitrogen. We also have an ethyl group on our 1, 2, 3, 4, 5 carbon chain. Again, we have a 5 carbon chain. We have an amide functional group. So starting out, we have for 3 substituents, naming them in alphabetical order. Here we have an isopropyl group. Here we have a methyl group. And here we have an ethyl group. Ethyl comes first, that's at carbon number 3. So we have 3 ethyl. And then attached to our nitrogen, we have an isopropyl. I say isopropyl first because I comes before M. I comes before M, so we have N isopropyl. And we have N methyl. So 3 ethyl, N isopropyl, N methyl, pentanamide. For the next one, for our parent chain, we have 1, 2, 3, 4 carbons. So that is butanamide. We have a methyl group attached to the carbon number 3. And we have a sec-butyl group on our nitrogen, and that is a stereospecific sec-butyl group. So that carbon right there attached to the nitrogen is a stereocenter. I'm going to draw the hydrogen in. Attached to this carbon, which is our stereocenter, we have nitrogen, which wins. Ethyl is second, methyl is third. So this has a counterclockwise rotation, or an S stereocenter. Looking at our sec-butyl, the B in butyl comes before the M in methyl. So we have S and then N, sec-butyl, and then we have 3 methyl butanamide. And ideally there'd be a little bit less space there, but hopefully you see what I mean. All right, now for the following esters, name the following esters using IUPAC names. This is remarkably similar. For an ester, we're going to take off the E of our hexane and add O8. So in this case, we have 1, 2, 3, 4, 5 carbons. So this is pentanoate. We also need to specify the group that we have attached to our oxygen. So in this case, we have an isopropyl group attached to our oxygen. So this is going to be isopropyl. This is always going to be the first word, so there's no alphabetical specifications there. Essentially, what is attached to our oxygen of our ester is going to be the first word, and then we will alphabetize substituents attached to the parent chain. So after our isopropyl group, we have 1, 2, 3, 4, 5 carbons. So this is isopropyl, and then space, pentane, and then instead of an E, we add O8. So isopropyl pentanoate. In this case, we have an ethyl group attached. So ethyl comes first, and then we have a space. So in this case, we have ethyl. And then for our parent chain, we have 1, 2, 3, 4 carbons. This is carbon number 1, carbon number 2. We have a methyl with a stereocenter attached. For this, the stereocenter always comes in front. So here we have carbon number 1, 2, 3, 4 is in the back. So this is a counterclockwise rotation. So we have S. And then we have, again, our methyl at carbon number 2. So 2-methyl butanoate. For the next one, we have an isobutyl group attached to this oxygen. So that's going to be the first word, isobutyl. So an isobutyl group attached to the oxygen. And then for our parent chain, we have 1, 2, 3, 4 carbons. So this is going to be, we also have a methyl group at carbon number 2. So 2-methyl butanoate. For this carbon, we need to start out by naming this carbon chain, which is attached to the oxygen of our ester. So here we have carbon number 1 and carbon number 2, which is a stereocenter. We have a hydrogen going in the back. CH2 is tied with CH2, which both beat that. So that one's connected to an oxygen. That's 1, that's 2, that's 3, that's 4. So this has a clockwise rotation, or an R stereocenter. So this is going to be 2-methyl, and then 1, 2, 3, 4 carbons. So 2-methyl butane. And we said we had an R stereocenter there. So R2-methyl butane. And then we start out with the parent chain, which is 1, 2, 3, 4, 5 carbons long, and a methyl group at carbon number 4. So 4-methyl pentanoate.